Alright, so this problem's cool just because you have, again, two different accelerations going on. One where you don't have acceleration and another one where you actually do. So here is the situation. Whenever you're doing this, it's always nice to kind of figure out what's going on with a picture. Do you have to do it? No, but it really does help visualize what's going on. Now, there's no way of me checking now since we're online, but it really is good exercise. So here's my race car, and it's traveling awfully fast, 90 meters per second, and it sees an accident occur really far away, 400 meters. Okay, his reaction time is 0.2. So this is the first part of the problem. His reaction time is 0.2 seconds. So that means it took him that long just to push down on the brakes. So, or she. So the race driver hits the brakes right there, and then it's going to come to a stop, or at least try to. The acceleration here is negative 8.0 meters per second squared. So that's deceleration. That's negative from the other way. And we want to know, does it stop in time? So we want to know if this d plus this d will be less than that d. So we're going to have two problems, and I probably should have done different colors. So we'll just do this one as pink and that one is blue. So we'll do this part first. So the blue part is constant velocity or zero acceleration. So d equals vct. If you want, you could also set up a matrix or variables right here as well. I usually don't, just because there's only like two things, and also you don't ever have to choose what equation to use since there's only one. So it's not really necessary. So here you have 90 meters per second times the time, which is the person's reaction time. And you just multiply it. So the time for that person to even push down on the brakes was 18 meters. So it took 18 meters just to start slowing down. Then on the other parts, you have VI, VF, ATD. And once again, we're looking for displacement. We know that the acceleration is negative 8.0 meters per second squared. Before it was all 9.8, but this object is not in the air. It's traveling in the horizontal direction versus vertical, so gravity does not play a role. We know what VI is. It's the initial velocity right here, which is 90. So this velocity, even though it hasn't changed, is still 90 meters per second until that person hits the brakes. So positive 90 meters per second. And the goal is to, I believe, come to a stop. So we want 0 meters per second. So we have 1, 2, 3 variables. We're looking for displacement. We don't care about time. So I believe the best equation is VF squared equals VI squared plus 2AD. Plug everything in. It's nice to have velocity 0. VI was 90 meters per second squared plus 2 times negative 8 meters per second squared d. Move the 90 over to the other side. Negative 90 meters per second. Actually, I should have squared it too. I'll just keep it like that. Equals, and I'll do this one, negative 16 meters per second squared d. I'll square this now. 8100. Let me just make sure. 8100 meters squared over second squared. The negative cancels out, divided by negative 16. Oh yeah, whoops, that negative is out here. I messed up. So let me see if I can erase it. I fooled myself. Like that. Because we're moving the whole entity over, the negative is on the outside. I apologize for that. So we get that. So 81 divided by 16. Get 506.25 meters equals d. So this number right here already is bigger than 400. So does the person come to a stop? And the answer is no. But most likely the person is slow enough, so maybe they could swerve out of the way. But if they couldn't swerve out of the way, they could not stop in time, and they're going to deck them. Another cool problem is we could also find out how fast the person was going right here, if we really wanted to, right? If we had this one, if we had 18 here, and we knew then this is 382, then you could just plug in 382 here and find final velocity, and you can know how hard this person actually hit. So that's pretty cool too if you wanted to know. All right.